Hello and welcome to part 7 of Dev Maths and Stats Refresher Course Lecture 9. And here you have a real treat in store because we're going to look at the best thing on the whole internet. So, as we shown in the last video, we don't need to assume we know the population standard deviation, which is good because we would never know that. So we can replace it with S, the sample standard deviation based on a sample. However, do we still need to assume that the variables are normally distributed? Often this is an assumption which is not reasonable. Many things that we care about in the real world, especially things like the distribution of any kind of property or income, is heavily positively skewed, or at least it's not normally distributed. It has some sort of very messy distribution, often very skewed. So that's not a good assumption. So we're now going to enjoy this lovely sampling distribution at this address, which really is quite fantastic. Totally cutting edge 1990s internet. So look at it, it's just fantastic. So here we have, let's blow it up a bit like this. You've enjoyed the stuff off to the side. Just focus on the actual goodies. That's what we need. So what you have here is a situation where here we have individual values which are distributed normally. So this could be the ownership of cattle in some rural area, or it could be incomes of new startups in the informal sector in a large city somewhere, or it could be the number of worshippers arriving. It's individual values observed and have a normal distribution. But what we have to assume in all of this is that this is unknown, only known to the creator or someone like this. We can't see this. So all we can do is we can take a sample, and if we assume that what you really want to know is the mean, so what's the mean number of cattle, mean number of worshippers per day, mean number of votes for this candidate, we want to know this. Can we get a good estimate of this just by sampling? So we get these amazing eye candy animations now. We're going to take a sample of 5 and also a sample of 25 below. And we're going to go for the mean. You can experiment with others. We'll just stick with the mean. It only goes up to a sample of 25 though. Here we go, animated. Look at that. It's picked 5, and that's the mean of the first 5, and now it's picking 25, and this is going to be the mean of the 25. It's almost done it. It's straining the processor. And there's the mean of the first 25. Okay. So the sample of the first 5 was here. Sample of the 25 was here. So we've got 2 samples, a 5 and a 25. So yeah. We can see that they're not far off. This one's a bit further off. This one's really close to the original mean. So this is the mean of that sample, that's the mean of the other sample. Now, of course, even though in real life you go and do one sample, in order to understand how close your sample is likely to be, or how close your mean is likely to be to this, what you need to do is think about all the possible samples. So if you did 5 samples, there's 5 and 5 there, 5 or 10,000 or 100,000. So that's taken 11,011 samples we've now taken and plotted the means. And you can see that with sample size 5, the means are in this sort of range. Sample size 25, they're here. That's already very powerful because it shows you that if you just do one survey size 25, it's very unlikely that your mean will be very far from here, because it's almost impossible that you're going to get a mean this far away, because all of them are in this area. After 100,000, you're never going to get one out here, which means that with the original distribution, if you wanted to know the mean income of people, we went and talked to people, you could by chance happen to talk to someone here. It's not that unlikely, or here. So you'd think, oh look, people are very poor here in this village, or they're very rich in this village, if you were unlucky enough to get one of these people. Even if you talk to 5 people randomly and take the average, it's almost impossible you're going to be this far away from the mean. And if you take to 25 people, it's almost impossible you'll be any further than that. So you really are narrowing it down very much onto the true population mean, even with a sample of 25. And when you get to a sample of 100, 1,000, you can get very, very accurate. And so even though this parent population is essentially millions and millions and millions of people, you only need to talk to 5, 25, 100 people to get a really accurate idea of where the mean is. Notice also you can be more precise than that. You can say, how much does this variation decrease? In this original one, the standard deviation is 5. So when I've got 25, the standard deviation divides by the square root of 25. So variance is divided by 25. Standard deviation is divided by 5. So I go from 5 down to 1 as the standard deviation. So it's 5 times less. And even 25 is not very big. So it's wonderful news. You can do the calculation. However, naysayers will say, no, that's no good, because in the real world, things are not distributed like this. This is just like mathematics fantasy land. You economists, you sort of scientific quantitative sociologists and impact evaluators, get real. In the real world, we know all about unequal power relations and distribution. We know that things are much more like this. Yeah. Now, what's going to happen now if you do your samples? You're going to get some crazy answer. Okay, well, let's try that. It's just such fun watching that. I wanted an animated one. Okay, look at this. So it does seem true. We're getting kind of a bit more of a random picture this time. So it's not going to work, is it? Because this skewed distribution is going to muck the mathematics up. Well, let's try 10,000 and let's try 100,000 and maybe another 100,000 for boost. So it's a couple of 100,000 reps. What we can see is that not only is even with 5, that skewness is starting to vanish, with 25 the skewness is just going, and it's still becoming very narrow and very accurate about the original mean. So this still seems to hold, even though the original is very, very skewed. When you do a sample, as the sample size gets bigger, it seems to be going back to normal, the distribution of the mean. But then the people in the audience that hate this kind of autistic, kind of nerdy approach and saying this is just not fancy. The real world is like this. It's not at all a kind of distribution. It's just really crazy. And I mean, you've got something like this. I mean, that's going to sort you guys out, isn't it? Okay, well, let's hit a few thousand reps. That's cool. It does, gets rid of it. You know, it still goes back to a normal distribution, even with 25. And normally people are doing samples of 100,000 or whatever. So it doesn't matter about this underlying population as long as you get a big enough sample. So that's the really great news. As long as you do the sampling properly and get a random sample, whatever the underlying population, the distribution of the sample mean becomes quite normally distributed as long as you have a big sample size. So that's, if you're churning through a stats book, you can see a proof of that, but you can prove that for any random variable, however it's distributed, as the sample size n increases, the distribution of that mean, the sample mean, gets closer and closer to what it should do, which is the normal distribution. Mean is exactly the same as the parent population mean, and the standard deviation, it gets reduced and reduced and reduced by dividing by the square root of the sample size. So as that gets bigger, this gets smaller, and you zero in on the population mean. So non-normally distributed data is not necessarily a problem, a serious problem, provided the sample size is big enough. Because if it's really skewed, then you need a big sample size. However, it's also provided that you do the measurement correctly. You haven't got biasing in the measurement, and you do the sampling correctly. Because if your measurement, you've got leading questions and so on in the measurement, recall problems, telescoping. If your sample is skewed because you just talk to people near the main road, or for some reason you don't get a representative sample because your sampling strategy does not get rid of bias. In that case, you might as well take my lectures and throw them in the bin, because that's not going to help you. If you get rubbish data, then nothing's going to help you. Well, it will, but this will not be true. But as long as you've got a decent random sample, the underlying non-normality is not a serious problem, as long as you've got a big enough sample size. So with that in mind, probably you'll now want to go back and play with that simulation again, but try not to spend all night on it because you have your families to see and so on. But in the next lecture, we'll put all this together and come up with some tests that you can actually apply to data. But for now, thanks for watching.